This is chapter 12, Earthquakes. In this chapter, we will have an introduction to the causes and characteristics of earthquakes. We will also look at the characteristics of seismic waves, and we'll explore the range of damage associated with specific earthquakes. And then we'll investigate how geophysics is used to explore the Earth's interior. Starting off with the Indonesian earthquake and tsunami. This was December 26, 2004. It was the strongest earthquake at the time to have occurred in 40 years. And what we see here is the epicenter. That's the surface above which the earthquake originated, and basically time in hours for which the tsunami traveled outward. So 1, 2, 3, 4, 5, and so on. And in red is the length of the earthquake rupture zone. Like I said, the black labeled lines are travel times in hours for the tsunami to radiate out from the earthquake zone. Now, tsunamis occur when there is a displacement of seawater due to rupture at a fault. That moves the seawater up. It has to go somewhere, and it can travel quite fast outward. This is somewhat even spacing of the travel time lines. Also note that the lines curve as the tsunami wraps around land masses. Now, this earthquake ruptured along a 1,200 kilometer or 760 mile length as a section of the Eurasian plate was uplifted, and the ocean floor above the rupture was lifted several meters. That caused the tsunami. The tsunami traveled about 800 kilometers per hour or 500 miles per hour on average away from the rupture. It arrived within minutes in Indonesia, and then 7 hours later it reached East Africa. How life was impacted depended on the population concentration along shorelines and distance from rupture. So obviously, the more people you have closer to this disaster, the more loss of life did occur. Over time, the wave energy was dissipated away from the epicenter. So these are some images from Indonesia. Essentially, a lot of this was green prior to the disaster, after which we had bare earth. Buildings and vegetation were destroyed in low areas by the wave. So just generically describing earthquakes, I mentioned the epicenter. That's right above the hypocenter, which is the actual location of the earthquake on a fault. If you extrapolate that up to the surface, you have the epicenter. So in this case, a rupture begins along a small section or point on the fault, which is the hypocenter. The first seismic waves that arrive at the closest point on the Earth's surface, that's your epicenter. So, causes of earthquakes primarily would be movement along faults. You have a transfer of energy through the Earth's crust. It moves on a fault preferentially, and you have an earthquake. We can have seismic stations that calculate the time that these seismic waves arrive. They'll arrive at a closer station sooner than a farther one, and scientists use 3 of them to triangulate the epicenter of an earthquake, figure out where it originated. So like I said, what causes most earthquakes is movement along faults, and that's an energy transfer. It could be a lot of different things in origin, but generically speaking, it's movement along faults. Volcanic activity can also generate seismic waves and result in earthquakes. You could have an explosive eruption that generates seismic waves, as does the movement of liquid magma. Also, movement along faults. You could have normal faulting occurring as blocks slide into an empty magma chamber, or a slope failure. If you have unstable rocks on the steep sides of a volcano, those can fail or fall down during shaking. I'll point out movement of magma as well. That's an energy transfer, which can result in an earthquake. Other things can cause seismic waves as well. Notably, landslides, say in Hawaii, that would be subject to massive underwater landslides from the volcanic activity there. And that's capable of generating large tsunamis through the displacement of seawater. Just in general, explosions, say if there was a nuclear test, that would create a distinct pulse-like seismic signal that can make the earth shake, the ground shake. Interestingly enough, we can use that to determine if anyone's testing a nuclear weapon on the planet. All right. So let's think about what happens before, during, and after an earthquake that's located along a fault zone. So, say through tectonic activity, stress increases in the region and rocks experience elastic strain along a fault. So you have increasing stress on the y-axis over time. Okay, and then with that, a fault will slip. There will be slippage on the fault. We see that in this diagram as well, with increasing stress over time. But once the earthquake actually happens and that fault moves, stress is going to drop because the force is dissipated. We'll see that in this diagram here, a droppage of stress, and then with increasing stress applied, you can see it go back up again and repeat the cycle. We call that stick-slip behavior because under stress, the fault sticks and then it slips again over time. All right, so earthquake ruptures. Under stress, we can have a rupture beginning as a small patch below the Earth's surface. With continued stress, it'll migrate out. It ruptures or breaks the Earth's surface, and we call that a fault scarp. Over time, it'll lengthen during an earthquake. It might look something like this. This is the Landers Scarp. It's like a tear in the Earth's surface. Or the same with the Bora Peak Scarp. That's Idaho. After the 1983 earthquake that occurred there. The Landers Scarp, that is the Mojave Desert in California after a 1992 earthquake. So we can look at this to observe where many earthquakes have occurred and their depths. So we say shallow is 0 to 70 kilometers, intermediate is 70 to 300 kilometers below the Earth's surface, and deep would be anything greater than 300 kilometers. All right, so what we see essentially is most of the broad range of depths here are occurring at subduction zones and arced areas. So you have Japan leading into the Aleutians over here, Java, Tonga. Earthquakes really do occur typically in narrow belts, and they coincide with plate boundaries, which are outlined in black. Mid-ocean ridges would have shallow earthquakes. Deep and intermediate earthquakes are, of course, in subduction zones. I'll point out as well the collision of India and Asia is still occurring, which is resulting in intermediate to shallow earthquakes across a broad region, and that's continental. Okay, so mid-ocean ridges, subduction zones, and transform boundaries. And continental collisions. We'll also point out we see shallow earthquakes on the interior of some continents. Well, in this case, all continents. All right, now the other side of the Earth. What do we see? A lot of yellow, which is shallow, right? Again, shallow at mid-ocean ridges. A range going from shallow to very deep at subduction zones. And relatively shallow at transform boundaries. And then shallow at the interior of some continents. This subduction zone, it extends, you see the earthquakes extending into the continent. A little less narrow than what we saw in the previous slide. That band of earthquakes is less narrow. All right, so earthquakes along mid-ocean ridges, we said those are relatively shallow. What we have here is an injection of magma. Magma intrusion beneath this area causes shallow earthquakes. You'll also get from that faulting near the rift. Shallow, medium-sized earthquakes would occur along the axis of that ridge where normal faults downdrop blocks. And then faulting on transforms, that is where you have shallow strike-slip earthquakes occurring along transform faults that are associated with the divergent boundaries there on the mid-ocean ridge. So how does subduction cause earthquakes? You have a trench and prism pointed out here. The oceanic plate bends into the trench as it goes down, producing earthquakes. We're transferring energy through earth materials. We also have this plate boundary. We call that the megathrust. And the thrust faults in the accretionary prism, when there's movement along those, that produces earthquakes. Our largest earthquakes are produced along the megathrust boundary. We have the deep slab as well. And volcanoes. So movement of magma in the crust above the subduction zone and related volcanic eruptions also produce earthquakes. So if you kind of put together the first several slides, you can get, movement along faults and further earthquakes associated with volcanism. There's a lot that can go on here. And that's why at subduction zones, we see a huge range of shallow, intermediate, deep earthquakes along this whole system. And what we find, like in South America, along the west coast of South America, when we triangulate the earthquake hypocenters, we actually find the geometry of the subducting oceanic plate slab like that. So deep, intermediate, and shallow earthquake hypocenters provide a lot of evidence for the theory of plate tectonics. And now to continental collisions. How could those cause earthquakes? They produce large earthquakes all along the megathrust and in the upper plate thrust faults. So here we go. Thrust faults, megathrust, plate boundary. And then continental strike slip faults can produce large but shallow earthquakes. Within continents, how could those earthquakes be generated? Well, you could have continental rifting causing shallow, moderate sized earthquakes along normal faults. Or you could have renewed motion on pre existing faults to produce large earthquakes, such as those in Missouri, the New Madrid area, major earthquake from 1811 to 1812. Rising magma can also play a part in that. Think of the Yellowstone hotspot. And then, of course, reactivation of old faults. Movement on those faults can result in earthquakes. All right, seismic waves. There's a few different kinds of seismic waves that are associated with this energy transfer through earth materials, resulting in earthquakes. So, fault movement, say, initially produces what we call P waves and S waves. Those P waves and S waves, they're body waves, and they travel away from the fault rupture. But when they reach the Earth's surface, some of their energy is converted into vertical and horizontal surface waves up here. So a vertical surface wave compresses materials, and we kind of see them traveling like ripples along the Earth's surface. You can have Rayleigh waves or Love waves. You could have a horizontal surface wave shearing materials like this. Almost looks like a transform fault movement. So how do we record those? I sort of hinted at it. The most basic way to record seismic waves is through a seismometer. This isn't exactly modern at this point. You have paper and a pen, traveling back and forth, recording movement, mimicking the way the ground is moving. Okay. A modern seismometer is an electronic device that records these motions along 3 separate axes and transmits the data to a centralized data warehouse. And then the digital signals can be printed out. So that way there are 3 main seismic waves of concern. P waves, which are compression waves, S waves, which are shear waves, and then surface waves. And although P and S waves originate and move away from a fault rupture at the same time, the P wave is faster, so it's going to be recorded first by the seismometer. A little more on our basic seismometer. We have this cylinder wrapped in paper. It rotates slowly at a known rate. A pen is suspended above the paper so that it draws a continuous line as the cylinder rotates. And the device is constrained so that the pen can only move back and forth along the red arrow directions. You can watch it work. So how do we determine the location of an earthquake? It's recorded by a seismic network. You have seismometers recording these waves. It's going to be detected on the network of stations the earthquake is. 3 stations have to be selected, and then the time between the S and P wave arrivals are measured and converted into distances. And the distances for each station are used to draw the potential location of the earthquake in any direction, which then makes a circle. The location of the earthquake is going to be where the 3 circles intersect. So in this case, we have an intersection right here. That's the location of our earthquake. But you got to have 3 stations. How do we measure the size of an earthquake? You've probably heard of the Richter scale. Um, so this slide shows one way to measure the size of an earthquake, and that is called the Richter scale. In the Richter or local magnitude earthquake scale, there's a relationship between the distance from the station and the maximum amplitude of the S wave and the magnitude of the earthquake. If you plot several stations that record the earthquake, we can then confirm the Richter magnitude. That's only one way. So you have on this plot distance versus magnitude versus amplitude. All right. So how can we predict what destruction arises from ground motion during an earthquake? Well, we can think about the rupture. Like I said, it's almost like a tear in the Earth's surface. It can happen along parts of the fault. And then you can have associated cracks in the Earth's surface that destroy buildings and roads. There could also be a landslide here. Mountainous regions can experience landslides, rock falls, and other earth movements. And then we'd anticipate structural damage as well. That depends on the type of construction. If you have a lot of concrete and masonry, those are rigid, so they're more susceptible to damage. Of course, it's going to be worse if we have something that's considered to be poor construction. I'm not an expert in that, but if you don't have a structure that can stand up to movement through it, of course it's going to fail. We can be concerned as well about, say, bridge failure in this diagram. If the bridges are too rigid or if they're built on unconsolidated sediment, because we have something called liquefaction. So if you have, say, near a coastline or a body of water, unconsolidated, water-saturated sediment, that loses strength and begins to flow during an earthquake when you have, energy being transferred through it. It can essentially suck things into it. Can be extremely hazardous. And of course, a tsunami in this area might also be a concern. It can cause damage along shorelines thousands of kilometers away from the epicenter. So, just for example, you have like Loma Prieta here. We're looking at some damage in these areas. And not only would the original earthquake event cause damage, but continued energy transfer through aftershocks can cause further damage. All right. So there are other things that can happen after something like this, after an earthquake. You can have fire, tsunamis, and other flooding. We have an earthquake hazard map in the lower left showing zones of potential damage. This is the Wasatch Fault Zone in Utah. And our highest damage risk is shown in red near the active normal fault zone system. If buildings are modified or were modified in this area, shaking damage to structures can be mitigated. So if possible, you want to improve building design. That's going to cost money, but this is a defense against, a natural hazard such as an earthquake. I'm thinking more about North America. We have some locations of major North American earthquakes, and those are the yellow dots, and then all these red lines are recently active fault lines, and I don't know how recent, but we'll just say that's what it is. So in general, we're seeing a lot more earthquakes along our recently active fault zones. So of course this is the Appalachian region. There's old fault systems here. located in New Madrid area and Charleston, believe it or not. It's not just the western U.S. that experiences major earthquakes. And we'll just kind of list a few out here. Northridge, 1994. Mexico City, 1985. Alaska, 1964. Hebgen Lake, 1959. San Francisco, 1906. Charleston, 1886. New Madrid, you might not have heard of that one before. So between 1811 and 1812, you had a magnitude of 8.0 on the Richter scale. That's pretty high, right? The death toll, I'm not sure exactly what it was, but if we had an earthquake of that magnitude in the area again, it'd be quite high because we have a higher population. You have a reactivation of old fault systems there, and movement on those faults causes a devastating earthquake. Same thing with Charleston, believe it or not. And we'll stop here for today.